Welcome, everyone. Today we're going to be talking about deep linear networks. We'll get to what that means in a second. First, we're going to take a step back and review some content from Watanabe's gray book, section 7.6. Also some content that we actually saw already in SLT High 1. Dan presented this during the primer. We'll talk about the learning process. Then we'll look at this paper by Jaco et al., saddle-to-saddle dynamics in deep linear networks. That's really the focus for today. And finally, we'll talk about SLT of deep linear networks. So can we estimate and maybe derive RLCTs for this model? Okay, let's jump right in. So to start us off, talk about the learning process. Down for a second. So in section 7.6, Watanabe draws this picture. Looks something like this, where on the left-hand side we have some parameter space. There are a few singularities. And on the right-hand side, we're plotting I think it was the Bayes generalization error, as a function of n. And he draws this picture where it's decreasing in a stepwise way. And the claim made here, and I think Dan has already pointed out multiple times that this is maybe the most conjectural part of the gray book, is that what's going on during the learning process is that we're hopping from singularity to singularity. Now, on its own, that's not a new claim. It's a claim we've been making longer. But this is actually a more particular claim where you're hopping from more complex singularities to simpler singularities. So over time, if you were to plot the RLCT, it would look something like this. And the statement here is that as you get more data, you're allowed to
maybe just to clarify, if you plot like the local
more
RLCT.
Yeah, that's a good point. So yeah, do we have actually?
Not really. You could you could put a hat there. Yeah, locals.
Yeah. Okay. Yeah. We need notation here. In any case, the idea is you get more data, and more data allows you to adopt more complex fits. And before then, you have this sort of Occam's razor style reason to stick to simpler functions. Okay. Let's look at the reason for this mechanism. Just remind ourselves. Well, in SLT High 1, Dan covered these two types of phase transitions. The first one were these type A phase transitions, at least until we have a better name for them. Ideas welcome here. Anybody does have an idea? And to see what's going on here, well, let's start with our favorite formula of all time. The free energy formula. Now, we've already seen that there's a local version of this, right? So you can perform the same integral over some subset of weight space. And for now, we'll take that as a given. And suppose you had a weight space with two singularities, right? So you have weight 1 and weight 2. Now these occupy different level sets. So that means that in this case, we're going to assume that the loss associated to weight 1 is greater than the loss associated to weight 2. It's higher than the second weight. But as you can see here, the RLCT is, say, smaller than the RLCT for the second weight. In this case, there are more intersections. Okay, so what happens? Well, you can just fill these values into the free energy, this local free energy formula, and plot them as a function of n. What you find is the following. As a function of n, we get these two plots. There's a transition, some critical value of n, where the minima exchange. So at the top, you see what we've plotted is n ln of weight 1 plus lambda 1 log n. On the bottom, we've plotted ln.
You want to attach his list now when you get up here.
Sorry, log n. Okay. So what's going on here is what Watanabe calls the universal phenomenon. I'll put it down here. So more data. Okay, I'll write it this way. Larger n, more data, allows for simpler singularities. Which mean more complex functions. Oh, running out of space. Okay, but we saw that there's also this type B phase transition. So I'll move at this point. So this isn't the only possible dynamic, the only possible phase transition dynamic we see in these models. That's because there are these higher order terms in the free energy formula. So, log n, this lower order term, is very slow. So for now, let's just treat it as a constant. And we're going to consider a different setup, a different collection of singularities. This time, they're on the same level set. So again, we have weight 1 as before, and weight 2. Now their losses are the same. Say the negative log likelihood's the same. But the RLCT as before, it's lower for weight 1. But now there's this higher order term, which is going to be greater for the first weight than the second weight. Well, as before, we can plot this free energy formula. It's a function of increasing n. And we see that okay, getting used to this. That now, eventually there's a transition from the more complex fit, from W2 to W1. And since the losses are equal, all we have to plot here is log n plus C1 And here we're plotting log n plus C2. So, depending on your higher order terms, you can have these phase transitions from more complex functions to less complex functions. And so I don't think we have a name as crisp as the universal phenomenon for this yet. But
the weird one.
This suggests the weird one.
Yeah, maybe it's worth saying that as far as we currently know, the main contribution to this the log n to, well, perhaps a significant contribution to this term is just the measure of the region itself. So if you have a solution which is represented by many parameters, that might be a reason why C1 is bigger than C2. Yeah, I haven't thought about this since the summit, but we really should try and find some examples where this manifests. Or maybe that's what's happening in toy models of superposition. I don't know. There's too many transitions there. Anyway.
It's not another idea. Not just volume, right? Sorry to. I can discuss this afterwards. Sorry.
No, go ahead.
That's fine. That's fine.
Just kind of thinking about Dan's comment that it's just about volume. It's more like, so if we are not already in normal crossing, then this is about. I think Dan's comment about the volume sort of applies in the already resolved, already normal crossing space. But in the original space, then it's not just about the volume.
Yeah, true. I mean, I guess we don't know what else is there, but I hadn't really thought about the contribution from Jacobian factors. That's what you're getting at, right? No. Okay. Anyway.
Not quite, but yeah.
Yeah.
Well, let's come back to the original slide for a second. I mean, what this suggests is if we continue this out a little further, after some point, you hit the set of optima, and you're moving around this set. And now you can have a transition to a more complex singularity. And so this should decrease now.
You're not going to make us wait to... Did you see this?
Okay, that's it.
Did you see this?
Well, this is the claim. This is not...
But you're explaining it.
No.
No, okay. Because you have these plots.
No, this is the setup. This is the background. We're still sort of...
Okay.
No. Haven't seen this yet.
Okay.
Okay. The conjecture, right? It's not going to be true for everything. Okay, so that's the Bayesian learning process.
Sorry, so I might have missed why you might expect is that combining type A and type B to get
so exactly. So at some point you sort of reach the optimal parameters, and at this point, your loss is going to be constant, but you can still make transitions if you stumble across a simpler solution. Again, conjectured. This is speculative.
Yeah, we should.
But at least
we should attribute the first part to the wise Watanabe, and everything after that dotted vertical line to the lunatics. In this
I'm confused because I mean I'm constantly getting confused between the Bayesian setting and the SGD setting, or the parameter-based learning setting. But here is another situation where your explanation of this was that we find the low loss solution, and then we kind of move around the set of low loss solutions based on finding simpler solutions. But I mean, this is posterior that is moving around, and when I think about finding solutions, that's talking about optimization. That's talking about SGD steps rather than increasing n or something like that. Whereas this story that you're actually sketching out of the phase transitions of the second type seems to be more like there's something in this lower order term, but that's like playing that's not, you know, standing in for optimization or something like that, right? I don't see any connection there. Maybe there's a connection, but you haven't made that case, right? This is just like some other kind of thing that looks like a march of the posterior, which is already integrated in all of the available information that you could get from Oracle optimization or sampling or something, because you're talking about the whole posterior on the parameter space. That is moving around due to some uncharacterized force of simplicity trading off against this C1, C2 business. And that's a different story from finding simpler parameters during you know, a search process, right?
Well, in principle, but
Yeah.
it could be related. I mean,
they could be related.
Of course,
okay.
the further we go
That's
down the
true.
asymptotic expansion, the more we doubt that we are confident about the relations between SGD and the Bayesian posterior. But yeah.
Yep. Okay. That was the Bayesian picture. What about SGD? So this is 1.2 SGD learning process. Okay, so what's going on here? Well, I mean, we've known for a long time that what's going on with SGD is something like, you know, you fit more and more complex functions. So if at first you converge to something sort of linear, then you start fitting the rougher trends, and at some point you start overfitting. So this idea that in a learning process you learn functions of increasing complexities is not at all new. The real question is, to what extent is this choppy? Right? Is this a process that's continuous? It's slowly becoming more and more complex, or are we making jumps like we expect from the Bayesian picture? There's at least some evidence to think that it could be choppy. So consider a very simple example. Linear regression. Right, so if this is supposed to be the loss function, what you find is there's this exponential separation in learning speeds. Right, so your convergence along each direction is going to be according to some exponential rate given by the curvature in that direction. And so because it's exponential over long time periods, you see that it basically first learns the first component, then the second component, and so on. So linear regression plus SGD means learning one component at a time. Okay, but that's a very simple example, right? Can we go more realistic? And I think you can see the rest of today when we're going to talk about deep linear networks as maybe the next step up from this, the example of linear regression towards neural networks. In any case, though, there's at least some precedent for expecting this process becoming more and more complex to occur in chunks. Okay, but can we say more? I think we're going to head to the next set of boards. Yeah, let's move to next set of boards and then come back. Or I can clear our board. Sure. So saddle to saddle dynamics and deep linear networks. So this is Chico et al. 2022, I think it was. Okay. So the basic idea here is going to be take a neural network and throw out the nonlinearities. Oops. Now, I know what you're thinking. If you throw out the nonlinearities, well, if you have a bunch of linear transformations and you stack them up one after the other, you just end up with another linear transformation at the end. So with respect to expressivity, this doesn't bias anything over linear regression. However, with respect to dynamics, things are going to get a little more interesting. And that's where this saddle-to-saddle dynamics picture comes in. Okay, we're going to see exactly what that means in a second. For now, let's just set up the problem in language more familiar to us. So we're going to define a deep linear network. Unfortunately, of course, they're using notation different to what we're used to, so everything gets mixed up. But we're going to stick with their notation because we're going to look at some figures in a second. But a deep linear network of length L and width N0 is some function, parameterized function, from R to the N0 to R to the N sub L that maps a vector in R to the N sub 0 to the product of a bunch of matrices times that X. So this is what we'll call the transformation. Right, it's just another matrix at the end of it all. This is parameterized by theta is this tuple of matrices. We're going to initialize the components from a Gaussian. So let's write it this way. According to some Gaussian. Now, to make things easier for us, we're going to restrict our attention to a special kind of deep linear network known as a rectangular network. So these have a fixed hidden layer width. So we call them LW, D-lines. And what they have is N1 ... up to N L minus 1 equals some fixed constant, which we'll call W. In practice, what we're going to do is for this initialization, we're going to sample it from we're going to sample it according to a parameter that depends on the width to some power gamma. And so the first contribution of the authors is to study what do the dynamics look like, what does this model look like for different choices of gamma. We're going to be more interested in the more conjectural stuff, but they have some proofs, and they showed new limits that haven't been studied before for what this behavior ends up looking like. Okay. Well, Dan, is it impossible to squeeze in figure 2 here, or should we go back?
Yep. No, I can put it here. I'm not sure which one is figure 2 exactly,
Has
so
Dan disappeared?
I'll put... Oh.
Then you have to come back to the orb. I accidentally kicked you away.
All right.
How'd you do that?
Yeah, I'll ask you about that later. And,
Secret.
and think up some suitable retaliation. But for now, I will attach an image. Is this the right one?
Okay.
Or?
Yes. Yes, I think so. It doesn't really matter what order we do them in, at least for these two.
Okay.
Okay. So what are we looking at here? We see these 3 plots. So these are for different choices of gamma. So remember, we are sampling each weight. Sampling the weights in layer I, j, k from this Gaussian up to this power. Okay, and so for different choices of gamma, you're going to get different dynamics. And I see they're labeled. So it turns out that for gamma smaller than 1, we're in the neural tangent kernel regime. So you can, well, we'll come back to this in a second, but you can see that because what we're looking at here within each graph are different choices of W. So as we increase the width, you see that the dynamics are becoming more and more regular, right? They become more and more exponential.
Mm.
And so this is equivalent to the dynamics becoming more linear, which is exactly what we expect to happen in the NTK regime. For small enough models up here, there's still this weird sort of kink happening, but for large enough models that vanishes completely and you're in the NTK regime. Okay, for the second picture, one was called the mean field regime. So this turns out to be more generally equivalent to Greg Yang's mu parameterization. And again, well, if you look very closely, you'll see that even for larger models, there's a kink there that you can't get rid of. So there's one transition, there's one phase changey thing. We'll make that more formal in a second. And it's easier to see maybe on this inset. But that's true for all model sizes. And you can't remove that just by going to larger models. And for gamma greater than 1, which is the saddle-to-saddle regime, that's the focus of this paper, you see that the plateaus, you can't get rid of them. And now there are many. And the other thing you notice is that as the number of weights increases now, those plateaus get longer.
Mm.
So this period gets longer and longer. Okay, so those are the salient features to look at here. Right, on the y-axis, I mean, it says train error. The specifics of this task are, if I remember correctly, they generate some true model. So let's call it A star. The truth is this matrix, right? Increasing numbers down the diagonal and they do that to make certain of these components more important than others. So the 5 will be more obvious to the learning dynamics than others. And then you just train it on mean squared error after running a bunch of random inputs. x sampled from, actually I'll put it like this.
So
You have 100 samples indexed by I, and the jth component are all in R5, sampled from, I think it's just this.
So you said N1 through NL minus 1 is W, and in this case, N0 and NL are 5.
Yep. Right. So, yeah, this is in 5, and then Y equals A star X I. That's also in R5. Right. So you come up with predictions, and you try to get them as close as possible to this Y. I need to figure out how to avoid putting my hand on the screen.
Just embrace it.
Okay.
And let your hand sit on the screen.
Yeah, I just embrace it. Just embrace it. Yeah, in any case, we can try to, let's move to the next board. We can try to draw a phase diagram, what's going on here. So I'll draw a box. So on the x-axis, we'll plot gamma, and on the y, we'll plot w. So this is going to be 1. Up here, we'll go off to infinity, and over here, 1 minus 1 over L. Remember, L is the number of layers. Okay. So there's this transition between these two regimes. Okay, so as we saw, the NTK regime is going to be here. Well, in particular, it'll be in the corner. Oops. The mean field regime is actually in this limiting case of the number of weights going to infinity. But more generally, this is the mu parameterization. And then on the right-hand side, we have the saddle to saddle regime. So that's what's going on here. You only get the crisp transition when the number of weights goes to infinity. Otherwise, it's going to be some smoother, more continuous thing. But in any case, it's nice that we see these 3 different approaches unified in one document, in one phase diagram. So the authors in particular focus on this point, right? So the weights going to infinity and gamma going to infinity.
Width.
What does this mean? Yeah, the width going to infinity. Well, I mean, I guess this entire line is the number of weights going to infinity up here. And what happens here is, well, think back to the definition of gamma, right? This sets the scale of initialization. So as gamma goes to infinity, the initialization scale goes to 0. So the weights will, I'll write this, will go to 0. You get closer and closer to the origin. It turns out there's this saddle at the origin where you can show formally that the dynamics are going to look something like this. So at the origin, there's this rank 0 saddle. And we initialize very close to this point. What happens is that the saddle will, the point will escape the saddle, and the escape time will become slower and slower. It diverges as as this goes to infinity. So I'll write that here as well. The escape time goes to infinity. But if you reparameterize time in the right way, then you find that there's always a way to escape. And what happens is you end up at a rank 1 saddle. And this part of the work is formal. They prove that this is possible, and they show exactly what the escape time is going to be. It's going to scale like as a function of L and the other parameters in the model. The less formal bit, I should say, I guess the more empirical bit, is what happens afterwards. So, the authors conjecture that the same thing will hold as you move to a rank 2 saddle and all the way up to a rank K saddle.
Since it might not be standard terminology, maybe just to say what a rank I saddle means. So this is meaning a sum of I squares,
right.
I presume, with the rest of the coordinate 0. So this is what we're often calling minimally singular. So it's a saddle. I mean,
I think actually using
it's a bit of a weird terminology. Because
I think it's slightly different.
Oh, really? Okay.
So it's just like it refers to the rank of matrix you're fitting.
Oh, right. Yeah. Okay.
So at the origin, your, let's call it A0 for the starting point. It's just a bunch of zeros, right? And then you learn, yes, A for some T. You'll learn one component, and then the rest will be basically 0. And so on. So it's about the rank of the matrix that you fit.
Yeah, this literature is it like non-strict saddle or something? There's some terminology. I mean, usually in differential geometry, you would refer to a saddle as a non-degenerate critical point, which has at least one.
Yeah, exactly. So I think that's the terminology they use. Non-strict saddle is then
right.
It's not a saddle. I mean,
yeah, it's like a saddle in lower dimension and then some zeros.
Yeah.
Mm-hmm.
Yeah, and the way they go about proving this is you show that, so you do this in 1 dimension. So you do the first, let's focus on this. You focus on learning this in 1 dimension, and then you embed it into a deep linear network of W equal to W0 plus 1. So you increase the width. And then that you've reached a minimum in this first component of the matrix. Write it down right here. Very clear. So in the other direction, you're probably not going to be in a minimum anymore. So you'll be at some saddle. And then you continue this process. Somewhat. Anyway. Okay, so yeah, this is the first part is the actual, the formal contribution. And then the second point is the conjecture 3, the saddle conjecture, where they expect, they say, oh, why would this process stop after the first saddle you've reached? Mm-hmm. You should find some new direction along which you can escape, and then approach a new saddle. There's a bit more to this escape. So I'm not going to go into this in too much detail because I think the saddle conjecture is the bit that's most interesting to us. But you can show that the escape is close to optimal, right? So there's some direction along the gradients along which the escape time will be optimal. It'll be as fast as possible as you're able to escape. And they show that the escape is very close to that optimal time.
The escape, you mean experimentally observed, or
Yeah.
what?
No. So again, what are the assumptions here? For when the width is 1, you escape the saddle at the origin close to optimally, and they show that this is within. I can't read my notes. Yeah, there's some direction. Let's draw it like this. So if going along this direction would lead to you escaping the saddle as quickly as is possible, then you're escaping along some path very close to it, and as quickly as it, and they can show this theoretically. They prove that this is the case. Okay. Let's look at the next picture.
I mean, you're drawing this in the same way you drew this picture before, but that's misleading because this is not a single level set.
Yes.
Maybe we'll erase some bit in between and put some dot or something. Yeah.
I did put that in my own notes, but I forgot to do.
Yeah.
Yeah, I think something else to emphasize, right? Like, I guess for this, right, these are saddles, so they're also slightly different than what we usually have in mind. Oh.
Yeah.
Yeah. Okay.
Surely we can. It shouldn't be too hard to classify the phases for a deep linear network, and just. I mean.
I don't think so. So we'll get to that at the end. A little call to action for all the theorists sitting here. Okay. Can you put up the next figure?
Yep.
Doesn't really matter which one. I guess the.
You didn't give them to me in an order, so it's lucky dip.
Yep. Great. Perfect. Okay, so what are we looking at here? Let's focus first on this one, the top right. So again, this is on the x-axis, the number of iterations, and on the y-axis is this MC loss. So this is a slightly different learning setup. So what you do is you have this true matrix, and you sample the components from some Gaussian. I don't remember what sigma is. I'm sure it's 1. And then what you do is you observe n entries. So you receive this masked snapshot of this true matrix. And so you train on the MSE between these snapshots, between these entries of A star and A theta. It's kind of weird, but yes, it works. And again, you observe the same kind of dynamics where it goes through these plateaus, right? So these things clearly look like phase transitions. Are they really? Well, I don't know. I didn't actually get this particular task up and running. I looked at the other one, but maybe they are proper phase transitions from the SLT perspective. Work to do. Now, this is for, I think, gamma equals 2.0. The picture we get below here is as gamma goes to infinity. And so it's a speculative image. And what they're emphasizing here is that the duration of these plateaus diverges. There are still plateaus, or at least you can show that there's this first plateau that corresponds to visiting the first saddle, but you're never going to see this on finite time scales, or you're never going to see this without reparameterizing your time. Okay. What's going on in the top left is, I think they've done PCA.
Ah, okay.
So one sort of random question, just because you sort of you mentioned the like tensor program stuff, and I remember Greg Yang with ABC parameterization kind of claimed that if you go above the mean field, that like you get like unstable training or whatever. But why in this case do we see stable training, I guess?
Stable training. I'm not sure.
Yeah, I feel like I'm probably confusing something there, but I'm not sure what.
I think above the mu parameterization, I don't know if his notion of above is the same one we're using here. These authors are parameterizing things differently, I think.
Yeah, I can look.
Right. So maybe that's it. So Greg Yang is also looking at, I think, also parameterizing the learning rate correctly. And here, it's actually an important point, we're looking at gradient flow dynamics. So at least the theory holds for assuming that the step size goes to 0. You've got these continuous dynamics. So maybe that's the reason it's stable. I don't know. It's an attempt at an answer. Danny, do you have something you want to observe?
Oh, I just hadn't thought about this top left picture, and now I'm all excited because I'm thinking it looks just like the thing in the induction heads paper.
Ah. So let me tell you about this top left picture. Okay, we've done a kind of, I think it was PCA. I think it was just a standard, dimensional reduction technique. In blue, you have the SGD trajectory.
PCA of what?
Yeah, of the gradients.
Of the gradients. Okay.
Let me pull up the picture of it here. Oh, audio just cut out. Am I still here?
Yeah.
Okay. Yeah, it's the projection onto a plane of the gradient flow path, theta sub alpha. So this is the gradient flow path in parameter space, and of the sequence of 3 paths. Okay. So yeah, it's no, not of the gradients, but of
the sequence of weights
of the path in parameter space.
Yeah.
Yeah.
So it's the same. It's the same as what's in the induction heads paper. Yeah.
Yeah.
More or less.
Exactly. Oh yeah, I see.
Well, they're doing it in function space, but yeah. Mm-hmm.
Yeah. And so this other line, these other components come from this greedy algorithm they introduce, where they explicitly learn only one component at a time. So what they do for this greedy algorithm is you start with one deep linear network, and you train that until it converges or for a fixed number of time steps. And then you embed that into a W+1 dimensional with deep linear network. And so you train that to completion. So you learn the next component and you repeat that. So this is explicitly only able to increase the rank one at a time. And they show, well, they look similar, right? These algorithms look similar. And so this leads to this this claim or this interpretation that SGD is learning according to this greedy kind of algorithm. Right? It's only learning one component of the signal at a time.
Mm-hmm. That's cool.
Okay. Okay. Let's do the next figure.
All right.
Okay, so, yeah, can you just put both up?
Yep.
Okay, let's focus on the second one first. We're gonna focus on controls, single board. Let's see a little better. Okay, so here they've just plotted more metrics over the course of training. So the first row, I'll just write it out so it's a little easier to see, looks at the rank. Second one looks at the nuclear norm, which you can think of as like a sort of continuous relaxation of the rank. And then the last one looks at the gradient norms. And so, well, I mean, look here, right? This sure looks suggestive. Sure looks like it's learning one component at a time. And I think if you plot them on top of each other, so if you plot the loss on top of this, you see that those moments coincide, just like you would expect. And the same is true in this continuous relaxation of the rank. You see that, right? So here it's kind of weird. You're already close to full rank, and it's, well, you see less of these steps, a fewer of these steps. But in the nuclear norm, it becomes clearer. But again, for these wider networks, it's in the NTK regime, so the dynamics aren't really interesting, and it just converges linearly. Okay, and in terms of the gradient norms, the thing to point out is that they spike right as you're going through this transition.
So I have a basic question about NTK. So why should I understand that larger weight initialization is somehow closer to the infinite width limit, which is somehow what this is supposed to suggest, but I don't really have an intuition about why it's so stark somehow.
Mm-hmm. I can give a sort of heuristic attempt. I don't know if it's right. I mean, there are plenty of results that say something along the lines of your weight norm is correlated with complexity. So a larger weight norm means more complex functions.
So all of these are infinite width limit, right? It's just like it's not that the NTK one is closer to the infinite width limit, right?
No, what I mean is that, okay, in the first column, the width 10 and width 1000 are much more similar than they are in the third column.
Okay.
So that is the justification for why gamma less than 1 is sort of the NTK regime, right? Because nothing less changes qualitatively.
I remember this is like a totally different thing, but this is kind of why I was struggling. But I know that the ABC, the paper which introduces ABC parameterization, like shows how the weight initialization scale effectively like differs between NTK, mean field, and other things, but the parameters are different, so I'm like kind of confused.
Okay, sounds like we don't have an answer. That's fine.
Yeah, not sure. Okay. So these sure look like phase transitions, right? Oh, wrong one. Okay. Oh, whoops.
Yeah, you hit audience. That's why I did that.
I see. Okay, there we go. Okay, so are these phase transitions in the proper sense of the word, in the SLT sense of the word? That's our last little point. SLT of the LNs. Before we come back to this chart that Dan put up, where you get a little sneak preview of what the RLCTs look like, let's talk about the degeneracies in this model. So I think there are two main things. So so first, the generic symmetries. Right, so which symmetries are present at every point in parameter space? Consider transformation T consists of a bunch of matrices, one for each hidden layer, where each of these transformations is some invertible matrix. Oh, oops. Right, we have W components here. Okay. Now, the way we're going to apply this transformation to our weights is we'll look at a little differently. We'll apply these transformations in between each of our weight matrices. So what we end up with is and so on. T1. Now just computing the resulting matrix. Well, you can already see where this is going. The adjacent transformations cancel out. Right, these cancel out. This will cancel out with whatever's next. And so you end up that this is equal to the original matrix. And so performing any invertible transformation like this in between these hidden layers is going to give you the same transformation. Now, the authors only focus on rotations. And so this is slightly more general. I believe this is because of a quirk of gradient flow dynamics. I think you end up with something like the norm of each of these weight matrices is going to be constant. It's something, maybe it's slightly different than that, but in any case, you end up being only interested in rotations from the gradient flow perspective. You know, if we want to be exhaustive, there are more symmetries here. But you know, these are generic, and the generic symmetries are less interesting than the non-generic symmetries. So the authors present this a little bit differently. They talk about inclusions, right? So if you embed a smaller deep linear network into a larger deep linear network, then you get these zero components that you can sort of move around freely. I want you to think about this differently. So if this transformation we're computing is not full rank, so if we can, you know, if it has the form, well, let's just treat it as block diagonal, where this will be R, this will be N. Wait, if it has rank R, then you know we have these zeros over here, and we can apply any transformation that leaves that null space invariant. So I'll write it down like this. Right, so as long as you perform some transformation of the hidden layers that doesn't change what's going on with these components that are sent to zero, well, your thing is, your transformation, your model is not going to change. Okay. So, I mean, you know, looking at this, if we now look back to this figure where we see the rank increasing, it's almost like trivially going to be the case that the RLCT should increase, right? Because we just, well, not trivial. It's not trivial the exact way in which it occurs, but we expect very strongly that RLCT is going to increase.
Sorry, we have performance for RLCTs of question, which I believe is
Your audio is a bit choppy, Matt.
Maybe you can write it out.
He'll be back. And his question too, presumably.
Okay. Guess I'll say something about the next point. So, all right, can we derive the RLCT? I guess the proper answer is I don't know, but
yes,
maybe. I'm sure we can, right? This seems easy enough.
Well, the Kale
So I just want to highlight what
it's a polynomial. It's an exercise. We can do this. Yeah.
Okay.
I mean, doing it for the phases,
Yes.
I'd have to think about, but yeah.
Sorry, Dan's grad students.
Sorry, I think I'm missing something. Is my audio clearer now?
Yep.
Yeah. So Aoyagi has the RLCTs of a reduced rank regression model since 2000.
That is exactly what we're going to talk about right now.
So,
Yep.
Yeah. So is this what's different about what you're asking for compared to that? Well, talk about it.
That is also my question.
Well, reduced rank regression.
You anticipated perfectly.
It's usually just the case L equals, I don't know what L was, but 2 matrices.
Yeah.
So
it's just, this is a special. It's a special case.
It's a special case.
Yeah. And does anyone know? Because I can't remember. Aoyagi has only done reduced rank regression, or has done, multi-layer reduced rank regression already. So, did we check that yet? I can check now.
I did not.
Please do check. If so, then this will have been a very productive seminar. We'll have figured out our answer. In the meantime, I'll pose the question. So reduced rank regression is a special case. Well, you can view it as a special case of a deep linear network. I guess I shouldn't write this down for DLN, where the number of layers equals 2. And so we'll just write it out a little differently. I'll write it out in the way that Aoyagi and Watanabe write it out. It maps some inputs to X.
I mean,
where this will be.
Oh, sorry. I will resist the temptation to jump in.
Please do jump in.
No, it's finish this part, and I'll say something about.
Okay.
Yeah.
Okay, so the rank, this thing will be equal to R, which, in this case, reduced rank regression, we're typically going to consider the case where it's not full rank. So R is less than W, less than this it's hidden with. So a few differences. What we were calling W before is now H. This is N0. This is NL. Okay, so Aoyagi and Watanabe back in 2005 obtain the following curse formula. r squared. It's supposed to be an r.
What do you mean when you say
and
where
minus-
rank W2, W1 equals R? You mean that's the rank of the true function, or?
Oh, that's actually a good point. We read it differently. Yeah, it should be of. Sorry,
W2.
it's called A star.
Yeah. Okay.
Of the rank of the truth, the thing you're actually trying to learn. That's n minus r. We're getting there. M minus r minus s. H minus r minus s. I'll use the line. Over 2, where zero is less than or equal to s, is less than or equal to minimum m plus r, h plus r. Okay, so we have a formula for lambda in this case.
I don't understand this formula.
So
it's a maximum of two things. One of them is an inequality.
No, sorry. This should be vertical line.
Oh.
So there's an s in this expression, and that s ranges from over this set, and so it's the maximum over all choices of s.
Let's see. Mm-hmm.
So here's the question to you guys. Who's going to generalize this? Edmund, Ben, in the audience, Jungtown.
No. We have a new attendee this week in the seminar, and clearly,
I see. This is the rite of passage, right? This is what hazing looks like. Meta. I mean, it seems like it should be straightforward. This really shouldn't be difficult. And in this expression, you only.
It's completely straightforward.
Yeah. Exactly.
Oh, all right.
Okay. In any case, before Simon has completed his mission, let's go back here. All right, so we can at least estimate the RLCTs in the meantime. And so I got Edmund's code online. A little shout out. Yeah, you better believe we can estimate the RLCTs. A few things to notice. So ignore this. It's the wrong scaling. It should be something like 8.5 here. I think 16.5. On the order of this, different runs give different numbers. It also depends on the size. It depends on the width as well. In any case, you see these very clear jumps, just like you would expect. And something to notice here, I've actually clipped the RLCTs to be positive. So, right, I should write, it's not very clear. This is lambda hat, right? And so in this estimation technique, you can get negative values of lambda hat. I think, Edmund, will you say something about this next week?
Yep, I will say something about that. But the quick thing is just that when you're close to some place where you are going to fall off a cliff, then that kind of thing will occur. The loss will falling off a cliff.
In any case, Edmund's going to talk about this estimation technique next week, so stay tuned. Yeah.
So did you tweak the hyperparameters at all, or you just took the standard ones in the paper?
No, I explored a little further. I think it got better regimes. Yeah, no, it does sometimes yield much worse estimates. So I did explore a little bit, but I don't think it wasn't very much. In any case, so this is the deep linear network. Why are we interested in this model? It's the next step up from very simple models and towards neural networks. It's a place where we can still compute the actual RLCTs. It's a place we can actually do the full SLT analysis and then compare it to observations from these techniques, from these estimation techniques. So I think it's an interesting area to look for, just to calibrate our techniques, to try to expand the theory. And I'm looking forward to seeing what the formula is for lambda hat here. Okay, thank you guys.
Thanks, Jesse.
Very cool. Thanks, Jesse. So Edmund and I posted some references in the literature, in the Discord. And there's a cluster of papers from Aoyagi and Watanabe around 2004 and 2005, which must be the one that you're citing as well. And these, according to the titles, just say reduced rank regression. So I doubt they look beyond that. But Edmund also pointed to a recent paper, a 2023 paper by Naoki Yoshida and Watanabe, upper bound of real log canonical threshold of tensor decomposition and its application to Bayesian inference. So it's only an upper bound of the RLCT, but that's like a start. I guess the idea is that this is tensor decomposition or something. I don't know what tensor decomposition is, but I assume it's just this.
It's a little different,
more
but
general.
Looks different, but might have similar technique.
Okay, yeah. Anyway, one thing to know is that upper bounds of RLCT are typically pretty easy in comparison to getting the precise value. But because all you really need to do is like some minimally singular analysis where you're just counting parameters. And even if you get a bound on the count, then you can get an upper bound on the RLCT. But if this is minimally singular, this deep linear network, then if we got the precise count, that would give us the RLCT. Is that right?
Yeah, I'm a bit confused actually. So I thought I'll have to check again what Jesse actually did in the appendix to our paper, but I believe reduced rank regression is minimally singular. So what that effectively means is that in the case where there's two matrices, once you extract this symmetry from the GLN action in between, there's nothing left. That's it. And then you get a parameterization in local coordinates. So effectively, you can just work out the codimension from that. Maybe that's not true with more layers, but I feel like having thought about something similar in connection with quiver varieties, that is it also. I mean, there's one other thing, which is that if you have a diagonal matrix with like, you can move that to the other side, and so that's but apart from that, I thought, anyway. So.
Yeah, there's like a braid group action, right?
Right. Yeah, but it's not going to be a continuous thing.
Yeah.
But actually I'm a bit confused even in the case with two matrices why more is necessary beyond just proving it's minimally singular. Maybe it's to do with the choice of the true distribution. Maybe it's not. Maybe it's only minimally singular when you have the true distribution being full rank or something.
Oh yeah, I was going to say that's the non-generic symmetries. Surely interesting. It may still be minimally singular because those might be particularly simple. I mean, they look kind of like the generic symmetries, but just on a subset of like a smaller part of the matrix. So
Yeah, so
It wouldn't
maybe I was underestimating the problem in my confident yes, which wouldn't be unusual.
Okay, but well, the other piece of evidence is
The
that
non-generic.
if it was easy for deep linear networks and tensor decomposition is sufficiently similar, then why is this Watanabe paper upper bound rather than
That's
just
right.
real log canonical threshold of tensor decomposition?
I want to point out that these non-generic symmetries are richer than the generic symmetries. You can apply any transformation to the null space.
You mean that T?
Yeah, I mean, like for the generic symmetries involve these invertible matrices, or maybe just orthogonal matrices. But the
I think I
richer.
want to interject a little bit and say that I think it's a little bit of a blind alley to get too hung up on computing RLCTs for deep linear networks. Like, then we know the answers, and so what? Right? Even this formula here, it's not like we're looking at this and caring deeply. So, I mean, if we can just show that it has the relevant behavior. I mean, if we could show all these level sets were minimally singular, that would be something, right? Because then we would. But like the numbers themselves, I'm not sure. Apart from calibrating lambda hat estimation, it doesn't. I don't really see a reason to care. So I agree with Jesse that this is an interesting case where people have studied dynamics, right? So seems to me the important aspect of this is that people do have some understanding of dynamics, which you could then compare to the kind of SLT phase-oriented story, and that even if DLNs are not like actually interesting beyond theoretical study, still would be a useful contribution.
It's worth pointing out as well that saddle-to-saddle dynamics is not unique to this paper. This is a well understood concept within the DLN literature. There are a bunch of papers that talk about the saddle-to-saddle dynamics. So I think maybe it's also worth studying just to try to get these people interested and excited.
I think, Simon, you had a comment.
So looking at the formulas in the IOIP Watanabe paper, I mean, there are, for instance, cases where the multiplicity is not 1. So it can be minimally singular. I mean, but not for full rank, as far as I can tell. So, for instance, if you have let's see. So if they're all equal and 3 and 4, yeah. So for instance, if you have so all size is equal, like what we're looking at, is 2 matrices, but the rank is n-1, then the multiplicity is 2. But if it's full rank, the multiplicity is 1. So.
Yeah. Okay.
Yeah, I'd like to say here are 3 alternative next steps to computing the RLCT in the multi-layer case. Alternative 1 is to, this is a question as well. Do these experiments, like, would they hold if we were just doing reduced rank regression? Well, maybe if you lifted the rank bound, the bound on the size of the hidden layer, but is there anything about these that requires it to be a very deep network? And if not, then we could maybe set up something where we're doing this thing, but then we are in the setting where we have the RLCT formula already. Proposal 2 is maybe you can just use upper bounds and they will just happen to be close enough to show you some interesting behavior. And I mean, you can plot an upper bound, which might be substantially easier to get than the tight bound. And then number 3 is we could using the kind of ideas in my master's thesis, which defines a rank for nonlinear transformations. We could potentially generalize this, look to generalize this beyond deep linear networks to shallow nonlinear networks at this stage, and potentially deeper nonlinear networks, and that might also be an exciting direction.
Yep.
I have a question. So I think this is a good test bed for the spectroscope that we're going to develop for detecting phase transition, because of how well developed it is, how well studied the dynamics is. But I in that context, I'm kind of also interested in understanding whether or not, when they say saddle to saddle, do they mean saddle? So we mentioned just now that these saddles include potentially zero eigenvalues.
What they mean is the saddle in some set of directions and the zeros in the other directions, and the saddle to saddle conjecturally, what they mean by that is that one of the zero eigenvalues becomes positive.
Right. Okay. So the reason I'm interested in is like I think we have already sort of think about this kind of things, because we kind of also want to define phases near saddles, not just local minima. And this could, I mean, we have sort of conjectured various mechanisms for that to kind of work. Like I won't go through them here, but I'm kind of interested whether or not the 3 RLCT lambda hat levels that are actually happening on actual saddles, like to meaning having negative eigenvalues.
They do.
Jesse, would you know?
Yeah.
I don't remember exactly. Dan?
Yeah, they don't have negative eigenvalues. I forget the term. I thought it was non-strict saddle, but what that means is that there's no negative eigenvalue, but there is a decreasing direction.
Okay.
So it's identical to the toy models of superposition situation, where you might at a point have a critical point where the Hessian either has zero or positive eigenvalues, but there's a decreasing direction.
Okay.
So that it's like, it's a degenerate critical point, so it's not a saddle, right?
Yeah.
By the terminology I would recognize,
yeah.
but it kind of in some sense is sort of like a saddle, except there's a decreasing direction, so it's not a local minimum. So that is the situation.
A soft saddle.
Or whatever. Yeah, so this is the kind of thing that we wanted to associate to phases, and which does behave like a phase, as you see in these plots. Yeah.
Okay. That is actually kind of interesting. That the fact that lambda hat works in soft saddle is kind of interesting. Yeah.
Yeah, this is definitely a technical point we need to resolve for the phase story to work. Yeah.
Yeah.
I guess we could continue discussing, but I want to make sure we have a bit of time to go around and talk about research updates. So maybe if there's one more question for Jesse before we finish. 3, 2, 1, 0. No more questions. Let's thank Jesse again. Thanks, Jesse.
Thanks, Jesse.
Thank you guys.
Jesse.